My name is Pawel, and I get the pleasure to tell you more about the Syglass technology. At the beginning I thought it's going to be more into the diagnostics and healthcare, but now, judging by the competencies and the broad spectrum of the interest in the audience, I changed a little bit the presentation to be more generic and tell you more about the micro elements that we manufacture. So, first I will introduce the company and the technology. I'll tell you more about the examples of what we can do with that, and I'll tell you more about how AI can help us design and bring part of this technology. We come from our heritage is from the additive manufacturing company called Syglass. We are a spin-off of them, and the company made most of the revenues from delivering high quality measurement equipment and additive manufacturing equipment. And from there, we developed the technology for manufacturing in serious production nanostructured elements. And it's important to understand the technology behind that, because it's much different what we've seen in the previous presentations. The biggest difference is that we manipulate the light inside the lenses, inside the core of the fiber, and not on the tip or not by implementing the lenses on the top of some surfaces. It works a little bit like Fata Morgana. So in Fata Morgana, you've got a difference in temperatures while the signal is, while the light is going through, and we applied exactly the same methodology, the same physics principles inside our optical elements. But instead of changing the temperature, what we change in our elements is the refractivity index, and we create this gradient in order to guide the light the way we want. And in order to achieve that, the features of these elements need to be at least 3 times smaller than the length of the wavelength of the light. So, for example, in this lens that is simply just focusing the light, we got several thousands of elements, but this shape can be arbitrary. So, how do we manufacture that? This concept is not new. We haven't invented nanostructurization of the optical elements. It was around for maybe 10 years already, but the process it was manufactured before, and in our judgment, it was why it wasn't commercialized. It was manual. So you had several thousands of individual glass rods with different refractivity indexes that had to be manufactured first, later cutted, cleaned, de-electrolyzed, and placed on the laminar flow machine with a physical worker assembling them according to the instruction, which is obviously prone to many errors and very time consuming. So we decided to automate that by applying our best skills for 3D printing. And the way we solve that problem is by 3D printing with glass, with 2 different types of glass. It can be custom, can be on the shelf. And we make preform, so-called preform, which is later used in the fiber drawing tower to make a fiber. So we print in macro to make later the nanoscale elements. And there were 2 major objectives while designing this machine, while solving this problem. One of these needs to be glass, so there is no polymer, no resin, it's directly melting the glass. And the second one is high scalability. And so we were afraid of falling into the trap of additive manufacturing that we will face later while raising funds or going to the OEMs with low scalability of our products. So here we can go directly from the custom design into the serious production. Why? Because we make this fiber, we can cut it already into thousands of active elements, whether it's special fibers or lenses or matrices of lenses. And I will start with the simple ones, so fibers. Powerful mixtures showed us that we can do lots of beam shaping. So here's an example also of creating, for example, a top cover, which is flat head in the fiber. So you can see that these cores can be arbitrary, can be square, can be hex, can be circle, whatever you want. And inside of that, we'll manipulate these refractivity indexes in order to achieve this arbitrary custom shape that you want. It doesn't have to be the beam shaping, it can be also for the communication. So, for example, we can make suspended core or anti-resonant fibers, or maybe if you want for some diagnostic purposes, maybe photonic crystal fibers as well. The next thing you can do, you can have the same structure and slice it into the finer pieces, so lenses. And these lenses are a particular feature that is very useful in creating more complex systems, because they are flat and you can join those elements together. So here we wanted to generate and show that you can generate complex structure. Here one is vortex, and the whole system is composed of a single mode fiber. Later we get a spacer. Later we get a lens that is creating this vortex structure, and at the end we get a green lens that is focusing the light. And that's all in one single fiber welded together. The feature size, we tend to merge the outer diameter to be with the single mode fiber, so 125 micrometers, but you can repeat them. You can set up any diameter you want on the fiber tower, and as per the core size, again, we can adjust to the desired feature. Usually it's between 5 to dozens of microns in the diameter size of the lens itself. The features in the structure are a couple of nanometers. The most complex structure we can make, we can take multiple of these pieces of fibers, we can put them together and repeat the process in order to achieve a matrix of lenses. Here you can see a matrix that is 2 by 3 millimeters big with around 600 lenses, each of them 80 microns in the diameter. The thickness of the element is 300 microns. So it's a great technology, very interesting, but what you can do with that. So our recent project, funded by Eurostars, is to help with diagnosis of many respiratory diseases like cystic fibrosis or chronic pneumonia disease. And the cells that you can see on the right-hand side are cilia that are found in the respiratory tract, and they are responsible for moving the mucosa, so the fluids down your throat because they are infected with some maybe bacteria or some dust. And it's important to measure how fast they are beating, how fast they are moving, because if they don't move in the right place, that means that it might be early sign of many of those diseases already. If you get these diseases, it is helpful to treat them. There are ways to do that, so the proof of concept is existing. What you can do, you can take a swab, you can put the cells into the petri dish, you can cultivate them, and later you can put them into the high-speed video microscope to measure and to see how far they move. But this procedure is not efficient because you need a patient to swab them. It takes several days, you need a technician, expensive equipment. So we're looking into the better way of doing that, and also the way that will allow into integration into existing healthcare system quite easily. So we can develop the endoscope and mainly imaging band and the endoscope system that will go directly into the respiratory tract and measure in real time the beating frequency of those cilia. And in the endoscope, you get several features. One is bringing the light and to shine the area that you are looking at. The field of view for us is around 7.7 millimeters, and the accuracy of the frequency may be up to half of the hertz. With this endoscope, you observe the real-time image at one wavelength frequency, and at the other, you're looking at the speckles. And with these speckles, you can analyze them to find out how exactly they are beating, how fast they are beating. There are more applications. We are looking into the bringing communication through clouds into the reality. So laser communication is facing the issue that you cannot send the signal through the clouds. Another example is the limitations of how many pores you can illuminate on a skin for the skin treatments. And there are lots of very interesting research problems. We are exploring many opportunities, but these are the low-hanging fruits for us that we are pursuing. And the last point that I want to mention is how AI can help us design the structures. Because you can see that they are composed of several thousands of elements. So in order to achieve the best results, we employ generative AI. And here you can see an example for the communication fiber that is helping us to split, design, to achieve the best results for example, thermal in the individual fiber. And I just want to thank the organizers that I could join this community, because it's a really nice event for us as a young company to find out what's going on in the market. And from our side, we are looking at partnerships and potential customers for applications and for this